Hi, I am Shan Namaz. We begin this lecture with the following corollary, and in this lecture we are going to introduce the freeness property of free abelian groups. This result states that if F is any free abelian group, then any two finite bases have same number of elements. If F is any free abelian group, then any two finite bases of F have same number of elements. But before proving this result, we have seen in the last result that if Zm is isomorphic to Zn, then M is equal to N. This is if and only if condition, i.e. if M is equal to N, then Z to the M is isomorphic to Zn. And conversely, if these two groups are isomorphic, then M has to be equal to N. So we are going to use this result in this result. So let F be any free abelian group. Free abelian group. Suppose x1 so on xn be any basis of F. Then by definition of free abelian group, we have F is isomorphic to n copies of Z. So if we consider any other basis having m number of elements, that is, also suppose say y1 through ym be another basis of F. Therefore, then F will be isomorphic to m copies of Z in this case. Now, the relationship of being isomorphic is equivalence relation. Hence, this will be symmetric as well as transitive. So, now if F is isomorphic to Zm, and say this F is isomorphic to Zn, means Zn is isomorphic to F. So using transitivity, Zn is isomorphic to F and F is isomorphic to Z to the power m. So using transitivity, we conclude that Zn is isomorphic to Zm. This implies that Zm is isomorphic to Zn, which further implies that M is equal to N. So this shows that any two finite bases of F have the same number of elements. Now let us define the freeness property of abelian groups. So let us consider an abelian group, a free abelian group F, and let x1 x through xn be a basis of F. so x1 x2 through xn. This is a finite basis of f. So let us denote this set which contain the basis elements of f by x. If we have any abelian group G here, so G is any abelian group. Now this x, this is actually a subset of f. So from x to f we have this inclusion map which takes xi to xi. Now if we are given any map from x to G, say this phi, G is any abelian group and f is given to be a free abelian group with basis x. So if we have a map from the basis set to any abelian group, then this map can be lifted to a map which is from whole f to G. Suppose this is phi and this is suppose psi. So then this psi is then this phi can be uniquely lifted to to a homomorphism from f to G. So this is actually the freeness property of free abelian groups. So this is the theorem. This is called the freeness property. Freeness property. So it says that let f be any free abelian group with basis say this set x is called x1 through xn. If G is any abelian group, if G is any abelian group and say this little gamma be a map from x to G, be any map, then there exists a unique homomorphism. Then there exists a unique homomorphism. Say this P from F to G, such that phi of, now this phi is from F to G, so phi of xi is gamma of xi. This is true for all xi in X. Now let us prove this theorem. So this is our abelian group G and this is our basis X. So we are given a map gamma from X to G, and from X to F we have this inclusion map. Let us denote it by I. So we can lift this gamma to this homomorphism, and this homomorphism, we have to prove this homomorphism is unique. So this is our diagram. Now this inclusion map is, since X is given to be a subset of F where X contains, so this is our F and this is our X. Now this X contain element is x1 x2 through xn, so this is our X. Now what this I does, it takes elements in X and maps to X in F, so this is F. So this the inclusion map, obviously this will be this map will be injective because it is inclusion, so it maps this xi to xi. In other words, this I it behaves as an identity map on X, so this is our inclusion map. Now by definition, since F is free abelian group, with basis X, which is equal to the set x1 through xn, it means any element, say A in F, let us do it like this, with basis X, then we have F is direct sum of x1 plus throw on plus throw plus direct sum of xn. So these are the cyclic groups generated by these xi's. So this is by definition of a free abelian group. So if F is direct sum of these cyclic groups, it means that any element A in F has unique, then therefore any element A in F can be uniquely expressed as so A has this unique expression, it is I runs from 1 to n, it is mi xi, where these mi's, they are the integers. So this is true for all mi's. Now we have to define this F, define a map this phi from F to G as this phi maps this element A to, now this combination here, this sits in F, so as sigma I runs from 1 to n mi gamma of xi. Now this element here, this is, so this is actually like this, m1 gamma of x1 plus so on plus mn gamma of xn. Now gamma xi is here, now this xi is mapped to gamma of xi, so these gamma of xi's are in G. Now G being abelian group, this means that m1 gamma of x1 is in G, m2 gamma of x2 is in G, similarly mn gamma of xn is in G, so their sum will be in G. So now if this sum is in G, this means this element is an element of G. Now to prove this phi is well defined, it follows easily because of the uniqueness hypothesis. So what do we mean by uniqueness hypothesis is that, so clearly phi is well defined. Since now to prove phi is well defined, since phi is well defined, so we had to prove, if we take a is equal to b, we had to prove phi of a is same as phi of b. Let a comma b belongs to f such that a is equal to b. This implies, now f being free with bases these xi, so this implies this a is same as sigma I mi xi. This is same as this b, and this b is can be expressed as sigma I runs from 1 to n. This is up to n. So this is say ki xi, where mi and ki, these are the elements of this set of integers. So this is the element b. So this means now since these two elements are equal, we have to prove their image is equal as well. Now phi of a, which is same as sigma I goes from 1 to n mi gamma of xi. Now these two elements being equal, this forces these mi's to be equal to ki's. So one can write here, this implies mi is equal to ki for all I. So this is phi of a is equal to mi gamma of xi. So this is same as I runs from 1 to n. This is ki gamma of xi, because if we set these two elements to be equal, this forces this inequality to be true, that is mi is equal to ki for all I. So this implies this is nothing but gamma of b, phi of b. So phi is well defined. Phi is homomorphism. So now to prove phi of homomorphism, we need to prove let a and b belongs to f. So a and b, they have these they can be expressed like these two expressions over here. So now phi of a plus b, we have to prove this is same as phi of a plus phi of b. Now this phi of a plus b is same as this is now this a plus b, this can be x, this is also an element of f. So this element can be expressed as sum of uniquely expressed as like this, say ti xi, because this a plus b belongs to f. This implies this is equal ti xi, where this ti runs from ti is in z. So this sum runs from 1 to n. So this is, but at the same time this a plus b is same as sigma I runs from 1 to n mixi plus sigma I runs from 1 to n this is ki xi. This is same as sigma I runs from 1 to n mi plus ki xi. Now since each element in f has unique expression, so these ti's will be equal to mi plus ki. So by setting these things in this equation we are done. So this is phi of sigma I runs from 1 to n, because a is same as and the sum I runs from 1 to n mixi plus sum I runs from 1 to n kixi. So this is same as phi of this is same as phi of sigma I runs from 1 to n mi plus ki xi. So this is same as sigma I runs from 1 to n mi plus ki phi gamma of xi. Also a plus b being an element, being an, so it is like this, element of f, we have a plus b is sum I runs from 1 to n tixi, where this ti belongs to z. So therefore phi of a plus b will be equal to sigma I runs from 1 to n, this is phi of, sorry, this is phi of tixi. This is same as sigma I runs from 1 to n. So actually we don't need this, we are done here, so why wasting our time? So we are done here. So this is same as sigma I runs from 1 to n mi gamma of xi plus sigma I runs from 1 to n, this is ki gamma of xi. So by definition of this phi, this is same as phi of sigma I goes from 1 to n mixi plus phi of sigma I runs from 1 to n kixi. So this is phi of a plus phi of b. Now we only need to prove that this phi is unique. So let us suppose, let phi prime from f to g, so this is over x here, this is g here, this is f here, this is inclusion map, this is phi here, sorry, this is gamma here, and this is phi here. So we are supposing that there is another such map p prime which is defined like phi. Suppose phi prime is another map from f to g, be another such homomorphism. With phi prime of xi same as gamma of xi for all I. Then this phi prime of xi is same as p of xi for all I. That is, this phi and phi prime, they agree on the basis. That means they agree on a set which is the generating set. So these two maps have to be equal. This implies that, so this is they agree on this set. So let us write one more step here. Or phi restricted on X is same as phi prime restricted on X. So now X being a generating set, so phi and phi prime, they agree on X. This means that phi is equal to phi prime on F as well. So the reason being, since for any two homomorphisms which agree on a set of generators, must be equal. So this completes the proof. So what we did, so if X is the generating set of F and we have any map from this generating set X to any abelian group G, so then if this map is defined on the generating set of F, so we can lift this map uniquely to a homomorphism phi from F to G. So this is the this is the freeness property of F. So we are done. Thank you.